All right, so today we're going to finish up that packet that we started yesterday. And we're going to need this for the lab that we're going to do today. So basically what you're searching for is this Q equals M delta T C sub P equation, okay? And on the assignment that I just gave back, never trust your lab partners, okay? Because I think what happened, there was a question on the back, and you had to calculate the energy involved, and there was a couple, two or three of you that just wrote down two of the numbers and didn't write down all three, and you all kind of made the same mistake. Here's the general rule of labs. You always assume that your lab partners are idiots. You trust no calculation that they do, you trust no answer that they give you, okay? You do your own calculations, okay? Literally. I've seen it more times than I ever want to admit. Somebody does something, somebody does a wrong calculation, and everybody in the group just blissfully writes down the same number, and it's wrong, okay? Never trust your lab partners, okay? I'm not saying that they're not good people. I'm just saying, when it comes to calculations, it's easy to make a mistake, and then everybody writes down the same wrong answer. Okay, so, and again, that you have to understand the difference between, and this is going to be important in terms of lab today, you have to understand the difference between temperature and energy, okay? So the temperature, if you go with the classroom analogy of Timmy, so a temperature is how much energy each individual Timmy has, okay? So you might only have 3 Timmys in the classroom, and they're all hyper as all get out, like they're strung out on Skittles, okay? And they're all bouncing, and I was like, wow, that's a lot of kinetic energy for each individual particle, okay? So that would have a very high temperature. The energy, though, is reflective of the fact that how many kids do you have in the room? What's the total energy of that entire body? So the kinetic energy part of it is a measure of, wow, what's happening with the individual particles. The energy calculation in joules is reflective of the entire system. How much energy is there in the entire combined system? And this is what this Q is going to represent. So if you look at what happens with the units, you've got grams. Okay, that's a key part of it. More mass that you have, the more energy that's going to take. You have change in temperature, which is in degrees Celsius. And then you have specific heat, which is joules per gram degrees Celsius. So if you look at what happens with the units, and this is why it's so important that you pay attention to this. Oh, your grams are going to cancel out. Your degrees Celsius will cancel out. You get joules. That's what energy is measured in. So if you only write down 2 numbers, you realize, wow, the units don't cancel out. Okay, this is why you have to have all 3 of these. So what you're after is this value of specific heat. Mass is easy to measure, okay? You're going to measure out, for today, for example, in the lab, you're going to measure out 300 milliliters of water, which is 300 grams of water. Okay, boom, that's easy to measure. Temperature, easy to measure. You're going to plug in a LabQuest, drop in a temperature probe, boom, temperature, easy to measure. Energy is tough to measure, mainly because if you look at all the LabQuest, the equipment that we have for those LabQuests, pressure, magnetic fields, voltage, all these different things, we don't have an energy probe, okay? I can't take a device and stick that in the water and go, oh, this is how many joules of energy that it has, okay? We can't do that. So what we do is we indirectly measure those things. So in science, there are certain what we call macroscopic things that we can measure. We all talked about pressure. Oh, we can measure pressure. Okay, that's cool. That's reflective of temperature. That's cool. We can measure volume. That's simple to do. Okay, but there are certain things that you can't directly measure. Entropy, which is the amount of disorder in the system. Okay, we don't have entropy probes. We indirectly measure it. Same thing with energy. We don't have energy probes, but we can indirectly measure that. So like when you all walk in the door, I can get an idea of how much energy that you have through an indirect observation. I don't have like an energy probe, but I can get a feel for what's going on. So that's the tough part about energy, is that how do you quantify the amount of energy that's in the system? So that's why we use that equation, okay? So you end up with joules because that's a measure of the energy. Temperature is a measure of the individual particles' kinetic energy, and that's a key thing to keep in mind. Okay, so when you get to this question 19, let's make sure everybody's cool. So you want to know how much energy, okay? As soon as you see the word energy, what are you going to try, what units are you going to end up in? Joules, okay? So you got 30 grams of water. Okay, there's my mass. Now, here's the difference. In this situation, up to this point, we've always talked about energy being put into a system, okay? How much energy does it take to warm something up? Well, the reverse happens when something cools down. When something cools down, then that energy is going to flow out of the system. So what we're going to do is we're going to go, okay, any change in temperature or any change in anything in any science class is always final minus initial. So in this situation, the final temperature is going to be 12.7, and then we're going to subtract 25. So what's going to happen is that that's going to get us a negative change in temperature, okay? So what that means is that, so we're going to have a negative change in temperature, multiplied by a positive mass, multiplied by a positive specific heat. So that means our Q value is going to be a negative number. So all that Q value, and this plays out large later on when you study more advanced thermodynamics and chemistry classes. If Q is positive versus Q is negative, that influences a concept of what we call enthalpy, which is how much energy that occurs per mole. So in this situation, you're going to get a negative value of Q. And all that negative sign indicates is that energy is flowing out of the water. If you have a positive Q, energy is flowing in. If you have a negative Q, energy is flowing out. So on this answer on 19A, you should end up with a negative number. It's a pretty straightforward calculation. You got 30 grams, there's your change in temperature. Since you're dealing with water, you're going to use a specific heat of 4.18 joules per gram degrees Celsius. So basically it's 30 times the difference in the temperatures times 4.18. Okay, pretty straightforward calculation. So when you look at this, on B it says describe the significant difference between the values and the energy values shown in Model 2. Okay, so first off with this one, because it's cooling down, one significant difference is the fact that this value is negative, okay, which means energy is flowing out. The other difference is that look at the value of the mass that's involved. This was 30 grams. If you look at what they did in the experiment, they did really, really small masses, like 2, 3, 4 grams. So because of the fact that we're dealing with such big values of mass, and also bigger change in temperatures, that's a pretty significant change in temperature. So when that happens, there's 3 things that are important if you're comparing those values. Number 1 is negative because energy is flowing out. Thank you. Number 2, there's a big mass relative to the calculations that you did before. And number 3, there's a relatively big change in temperature. So that's why that value is so much bigger than those ones that you had before. Okay? So that's what you're looking for on that one. Okay, everybody cool with what we've got so far? Up through page 4. We're good? Okay. So now, with this one, you have mercury and water. Again, here's when you're comparing things, it's vital that one of the skills that you have to be able to develop, whether it's in chemistry, biology, physics, whatever the science is, you have to be able to isolate what you're holding constant and what's being changed, okay? So that's going to be the key thing. So if you look at this, you got Hg, mercury, right? You got 100 grams. So what's common in all 4 trials? Mass. Okay, so we're going to have 100 grams, okay? That's going to stay the same. So if you compare trials 1 and 2 with the mercury, we put in 1,000 joules, we put in 2,000 joules. If you look at the water, that was 1,000 joules, that was 2,000 joules. So within each subset, the changes, the amount of energy that we dumped into the system was the same. So we're throwing 1,000 Skittles, we're throwing 2,000 Skittles. So that's staying the same in each trial. So one of the things you got, I cannot emphasize this enough, when you look at data tables, you don't get wrapped up in, oh, I'm going to answer the questions. No, step back, look at the data table, and go, what's being changed, what's holding constant? So I'm always going to have the same mass. Within the trials of the water and the mercury, I'm going to input the same amount of energy. And again, that input of energy is tough to measure because we can't directly measure energy. But what we can do is like, okay, hey, we know that this hot plate dumps a certain amount of energy per unit of time. We let it sit there for a certain amount of time, we know that's how much energy is flowing into the system. Okay. Now, so let's look at this. Here's your change in temperatures. So what do you notice about the change in temperature of the mercury versus the change in temperature of the water? Miles, which one has the bigger change in temperature?
Mercury.
Mercury does, okay? Mercury is a metal. It's cool. Back in the old days, you used to be able to have mercury in your classrooms, okay? But now they completely freak out if you do. Because my science teacher in high school, he had a bottle of mercury. We'd pour some out and we'd like bat it around. It's kind of cool. Can't do that anymore. They would absolutely flip out. Maybe because it's toxic, but small detail. So anyway, so the mass is the same. The mercury has a very large change in temperature. The water has a small change in temperature. So if you look at this in terms of this equation that says Q equals M delta T C sub P. So the masses are the same, okay? All right, let's compare this. All right, so let's compare trial 1 to trial 3, the mercury and the water, okay? Big idea. In both situations, the Q value is going to be the same. 1,000 joules, 1,000 joules. That 1,000 joules is the value of Q. So here's the deal. We got 1,000 joules, 1,000 joules. That's the same. The mass is the same. It's cool, right? Same mass, 100 grams. So since mercury has a big change in temperature, and we still have to get a certain value over there, so mercury has a big change in temperature. So what do you know about the specific heat of mercury? Is that going to be a big value or a small value? Mr. Peterman. Okay. I'm going to dump the same amount of energy into water and mercury. Okay? The masses are the same. Okay? The mercury has a big change in temperature. So what do you know about the specific heat of mercury? Is it a big number or a small number?
Small number.
Beautiful. Okay? Now, water's just the opposite. Water, I'm going to dump in the same amount of energy, same mass. Water has a small change in temperature. So therefore, it has to have a big specific heat. Okay? So what that means is that it's very easy to heat up mercury, but it's also easy to cool down. Water is tough to heat up, but it's also, once you get it warm, it contains a lot of energy that you can use to release that out. So on those questions, okay, a lot of them are pretty basic. 20, so help me, if you miss 20, I'm just going to flip out. What two substances are being heated for the love of all things physics, or chemistry in this case? Oh, mercury and water, that's tough. So on 21, compare any two trials and use the amount of energy that is involved in different systems. Is the temperature change the same or different in the two trials? Okay, go with that. So then, here's the heart and soul. Based upon the data, 4.18, use Model 3 to solve the value from the specific heat of mercury. So here's the deal. You know, Q equals M delta T C sub P. Pick one of the trials of mercury. It doesn't make any difference. Pick one. Pick the first trial, pick the second trial. It doesn't make any difference. you're going to know the value of Q. You know the mass of the mercury. You can find the change in temperature of the mercury. It's an algebra problem. Solve for the specific heat. So, and do me a favor, come over here and imagine there's a line where you're going to write your answer. If you just write down a number, so help me, I am going to completely flip out. Okay? Pay attention to the units. Okay? I cannot emphasize this enough. Pay attention to the units. If you just put, oh, there's my specific heat, 2.4. I have absolutely no idea what that means. I don't know if that's your GPA. I don't know. That the air temp, I don't know what that is. Pay attention to the units. Okay. Now, 24, that's an algebra problem. There's your value of Q. There's your change in temperature. Okay? What's the mass of the water? It's an algebra problem. Solve for mass. 25, it's the same idea. We're going to dump in the same amount of energy. There's my same change in temperature. Find the mass of the mercury. Then, on 26, you're going to try and solve for the specific heat. So, you've got your Q value, you have your mass, you have your change in temperature, solve for the specific heat. And again, pretend that there's a line over here and put that answer there. Okay? Are we good? Any questions at all? Going once, going twice. So stop that camera for a second. Okay. So the lab that you're going to do today is kind of like what we call like a lab final. Okay? So it's a culmination of everything that we have done up to this point. So what you're going to deal with, and they're pretty cool. These are called hot snaps. Okay? And right now it's a liquid. And within that, you're going to find a like little piece of metal. So to activate this, and right now this is all liquid, it's at room temperature. So to activate it, what you do is that you hold this and you snap that metal back and forth a couple times. So the first thing that you get when you get this, you're going to make an observation. You're going to say, oh, okay, right. It's a liquid. So that means that the particles are held together loosely. Okay, they're held together because it's a liquid. It's not a gas. So that means this is going to be important. There's bonds that hold the particles together, but not so tightly that they're locked up in a solid. Okay? So this is going to be important. There's bonds that hold this together, but it's not a solid. So it's like this Goldilocks zone. Somewhere between a gas, somewhere between a solid. So what's in here is water and a substance called sodium acetate. Okay? So sodium acetate, and we'll spend a lot more time talking about this chemical formula because acetate is one that we use a lot. And sometimes you'll see acetate, the formula for acetate written two different ways. Sometimes you've written C2H3O2, sometimes you see it written as CH3COO. The CH3COO is more correct because if you were to look at an acetate molecule, this is actually what it would look like. You've got one carbon surrounded by three hydrogens, so that's that CH3 part, okay? And we'll get more into this later, but carbon can form 4 bonds. So basically, carbon can form 4 bonds. So it's forming one bond with each of the hydrogens, there's 3 of them, and then it forms another bond with the carbon that's beside it. So then, on the end of this carbon, there's 2 oxygen atoms out here. So we'll get more into this later, why this is. But this sodium, this is going to be important in terms of how you're going to draw these structures today. The acetate is going to have a negative charge, so it has an excess of electrons. Attached to that is a sodium, okay? So that sodium out here, because it's an alkali metal on the left side of the periodic table, is going to lose an electron because that's what makes it more stable. So this is like a match made in chemistry heaven. The sodium wants to give up an electron, and the acetate wants to take it in. So it's like winner, winner, chicken dinner. Hey, I want to get rid of an electron, I'm going to become more stable. The acetate says, I need an electron, I'm going to become more stable. That way, everybody's happy, right? So, if you look at the sodium acetate is like a white powder. It looks like salt, okay? So, we've got this sodium acetate. And what happened, you'll see that sodium acetate is soluble in water. What that means is that it dissolves. Okay, we talked about that before. If something's soluble, that means it dissolves in water. So within this solution, we have what's known as what we call a supersaturated solution. So in other words, this thing is completely overloaded with sodium acetate. So there's water and a whole bunch of sodium acetate ions that are within this. So what's happening is that you have two different types of bonds. You have the water molecules, okay? And does anybody remember, does the oxygen end have a negative charge or the positive charge? Negative, because it's taking away electrons. So the oxygen end has this negative charge, and the hydrogen end has a positive charge. So what's happening is the water molecules are attracted to each other. So basically what's happening is that these kind of like stack each other like this. So here's these water molecules. So here's the positive end, here's the negative end. So the negative end of one water molecule is going to be attracted to the positive end of the other one. So sometimes, a lot of times they're drawn like this where they like kind of alternate each other. So this positive end here, this hydrogen, is attracted to that negative end. So imagine these being stacked like this. Water, have polar molecule, positive and negative end. Positives and negatives are attracted to each other. Now, so that's one type of bond that exists. And we can draw that as like a dashed line. Okay? Oh, there's a certain, they can move, okay? So it's a strong bond, but it isn't strong enough to hold them together as a solid. Now, along comes the sodium acetate. So here's the sodium ion, and this is positively charged. So, ramen, the sodium ion is positively charged. Which end of the water molecule is it going to be attracted to? The negative end or the positive end? Okay, fantastic, because opposites attract. So I can come in here and go, okay, hey, the sodium ion is going to be attracted to the negative end of the water molecule, and the acetate ion, which has a negative charge, is going to be attracted to the water molecule, okay? So what's going to happen is that you're going to have bonds here. So you're going to have two different types of bonding going on. You have bonds between the water molecules themselves, and that's what allows it to exist as a liquid. And then you have the sodium acetate, which is bound to the water itself. So you have two different types of bonds, within the water molecules and within the sodium acetate. Well, so what's going to happen is that, and you're going to activate this, and one of the things you talk about in science is what's known as an activation energy. So, an activation energy, here's the easiest way to think of it. If you've ever seen like a roller coaster, and so here's like your roller coaster, you go up the hill and then it starts doing this, okay? So, the easiest way to think of activation energy is that it's the size of the hill, okay? So activation energy is how high that initial hill is on the roller coaster. So if you're going to start the roller coaster, you have to get it up the hill, okay? If you don't get it up the hill, well, that's kind of boring. It's like, what's happening? We're just kind of sitting here. Oh, that's fun, okay? No. So, but you have to go completely up over the hill for this thing to get going. So once you get over the hill, then it's like, oh, this is exciting here, yay! Okay, they go, they're doing this, like, this is fun, right? So you can think of reactions in chemistry of kind of being like a roller coaster. So this, we call it U sub A, is our activation energy. That's the size of the hill, okay? So we get this roller coaster up the hill, and then once you get it over the hill, then you're storing potential energy, basically. So it's like a roller coaster. You're lifting it up, you're storing potential energy. Mother Nature doesn't like potential energy, so she changes into kinetic energy, and then you go down the hill. So what happens is that when you're going down the hill, people scream, go, ah, okay? That's releasing energy, okay? You're giving off heat. So here's a great analogy with what's going to happen, is that you've got this, okay? And you're sitting right here with some initial set of conditions, right? Okay? So what you have to do to start the reaction is that you have to get the roller coaster up to the hill. So to do that, you're going to take and you're going to bend, grab that piece of metal, and you're going to bend that thing back and forth. That's equivalent to lifting a roller coaster up to the top of the hill, okay? That's your activation energy. If you don't provide that activation energy, it's just going to sit there, okay? So just like a roller coaster isn't going to go anywhere unless you lift it up the hill. So by you guys bending that piece of metal, that's equivalent to getting the roller coaster up the hill. Now, then it's going to go down the hill. So what you're going to see, the reason that they're called hot pockets, oddly enough, is because they give off thermal energy. Okay, so you can use these as like, if it's really, really cold outside, people use these as like a hand warmer, so they'll activate it and they'll put it like inside their glove or inside their shoe or something like that, because it gives off thermal energy. So what you're doing, grab it, gets it up the hill, boom, slides down the hill. So what that means is that your products have less energy than your reactants do. And if you've ever been on a roller coaster, you know that's true. You're all excited. It's like, oh, I'm riding the roller coaster, cool, right? And it's going, lifting up, and you hear it going up, and like, this is cool, right? And you're full of anticipation, and then, woo, down you go, right? Everybody gets strings, like, this is fun, right? And then you get done, and you're like, oh, man, we're out, okay? Because you let all of that energy go. That's what's going to happen here. So what's happening is that we're storing energy in the bonds of this. We activate it, that energy is going to flow out. Now the question is like, how do we measure that amount of energy? What we're going to do is we're going to take advantage of water. So what you're going to do is that, and you have to have this sequence right. Do not bend this until you're ready to start. So what you're going to do is that you're going to measure out 300 milliliters of water. So you're going to get, that didn't go well, big beaker like this, okay? And you're going to come over here to the sink, and you're going to fill that up to the 300 milliliter mark, okay? Now, these are actually marked off two different ways, depending upon if you're pouring something out or if you're filling something up. You want to start on this side over here, where you're going to start here, and you're going to go 0, 100, 200, 300. Don't measure down to 300 here. You would do that if you had 1,000 and you were pouring out 300. You want to fill it up to 300. So go over there, get a beaker, fill it up with 300 milliliters of water. Now we're also going to try something new. I don't care which. I've got 2 of these styrofoam containers. So the disadvantage of glass is that it actually allows energy to flow out of the glass. Styrofoam works well because it keeps the energy within the system. So a couple of groups, okay, I don't care which groups. Here's what I want. You guys are going to be my guinea pigs. Okay, you'll be the first groups to try these, like out of the entire Chem 1 class. So if you're willing to do this, here's what I want you to do. Get the 300 milliliters of water and pour that into here, okay? So what I want to do is I want to compare the change in temperatures of the groups that use the glass beakers with the groups that use the styrofoam. So hopefully what we see is that this gives us an actual better picture of what's going on, because we're keeping that energy within the system with the styrofoam, and if we see a noticeable difference, then we're going to get more of these. So the groups that have these, okay, you guys are the guinea pigs. So what I'm going to do is I'm going to compare your results to the groups that have the glass beakers. I'm going to see if there's a noticeable difference in that change in temperature. So literally, you guys will be the first ones to ever use this. So here's the idea. You're going to put water in here. You're going to put 300 milliliters, beaker, styrofoam, whatever. Then you're going to measure, listen to me, then you're going to measure the temperature of the water. Okay? LabQuest Temperature Pros measure the temperature of the water. You're measuring how much kinetic energy the water molecules have. Then activate this, okay? Observe what happens. It's kind of cool to see, okay? Work that back and forth. You should see two very noticeable changes. You should see a change in the structure of this, and it should turn into a solid, okay? So if it works, it should change into a solid. Then you should obviously feel this energy. You should feel it getting warm. Now, here's the deal with bonds. If you break bonds, do you put energy in or do you take energy out? Think about melting ice. You all broke bonds. What did you do? Luke Etheridge.
We added energy, right?
Okay. So you break bonds, you put energy in. So if you form bonds, you release energy. So what's going to happen is that this thing is going to release a lot of energy. It's going to release a lot of energy because it's forming bonds. Okay? So put energy in, you break bonds. Release energy in the formation of bonds. So, and this is a very visual thing. So what's going to happen when you do this, you are actually going to see a change. Because you're going to see a change because this thing is going from a liquid into a solid. Okay? So to do that, you have to form bonds. That's the whole idea. Because if you don't form bonds, then it stays just as a liquid. So you're going to form bonds, and you will visually see a change in these. Okay? So you're going, oh, right, cool, right? So then what you do is you measure the temperature. What you want to do is record the highest temperature that you get. So we're not going to keep track of time. You're just going to kind of gently stir that liquid, and you're going to have the initial temperature of the water, and then you're going to have the final temperature of the water. So you should see the temperature of the water go up. So the idea being is that whatever energy is lost by the hot pocket is what's gained by the water. So what we're ultimately going to try and do, here's the big picture. The ultimate idea is that we're going to use M delta T C sub P. You're going to know the mass of the water, 300 grams. You're going to calculate the change in temperature because you're going to know the initial temperature of the water, you're going to know the final temperature of the water. And you're going to know the specific heat of water. So what you're going to figure out is how much energy was given off by measuring the change in temperature of the water. Now, so when you study thermodynamic systems, you talk about a system and you talk about the surroundings. So this is the system, okay? What we're doing is, we're going to look at what's going to happen. So what we do is we look at the water around it and see the influence that it has on the water, which is the surroundings. So this is the system, the water is the surroundings. Okay, so stop that camera for a second. So here's what you're going to do. So this is like a culminating thing. So the first page is basically a summary of everything that we've done. By the way, today's Wednesday. We're going to do this lab. We're going to review tomorrow. Big test on Friday. Okay, over gas laws and this thermodynamic stuff. Okay. So this front page is basically a lot of what the test is going to be. So you start off, to break bonds, energy must be either put into or released. Okay? You're just going to go through this. When you get to this graph on the bottom, okay, and this is a graph I just gave back. So you got A, boom, 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 boom. So what you want to do down here on question number 11, okay? I want to say describe what is taking place in each section on the graph. In addition, any phase change, note if energy is being used to break bonds or increase kinetic energy. So let's make sure everybody's cool with what I want. So you're starting here at -10, right? So this is going to be section A. So you can go from -10 to 0. So I'm dumping energy into the system. So in this situation, is the temperature changing on section A? Miles, is the temperature changing?
Yeah.
Yes, okay? So remember, temperature is a measure of kinetic energy. So on section A, I'm dumping energy into the system, okay? Temperature is going up, so am I increasing potential energy or kinetic energy? Grace? There you go. So right there where it says A, you're going to say, oh, temperature is increasing, I'm increasing the kinetic energy. Now, what's happening on B? You're at 0 degrees. Ethan, what's happening on line B?
That'll be potential energy.
And I'm going through a phase change because this is when this thing is melting. So this is a class. So on B, I'm dumping energy into the system. I'm going through a phase change. I'm breaking bonds. I'm storing potential energy. So that's what I'm looking for on that description. So basically, you're either putting energy in to break bonds and store potential energy, or you're putting energy into it to increase kinetic energy and raise the temperature. Okay? That's basically going to be it. That's what you want to lay out on each of those. Now, turn to page 2. Okay? So, this is going to harken back to what's going to happen when water is going to boil. So, you're going to draw 3 different phases. Okay? Water at 90 degrees, water when it's boiling, and then water as a vapor. So, if you model this, here's the water molecules. At 90 degrees, you're still with a liquid, right? But 90 degrees is pretty hot. So what's happening at 90, this is what I want you to be able to show, is that at 90 degrees, it's still a liquid. So you're going to draw on here, and I'm going to tell you, use dot as the individual water molecules. If you really want to get cute and make it look like Mickey Mouse, you can do this if you want. Okay, or you can just draw a circle, it's up to you. But here's the whole thing. They're going to be bound together, but they're going to be moving because it's like 90 degrees, okay? But it's still going to be a liquid. Now, then as it begins to boil, and you all seen water boil, okay? We did this in the lab. Y'all saw water boil. And you saw pockets of vapor form. So basically what's happening there is that when it begins to boil, you are now breaking the bonds that hold the water molecules together. So with this one, what I'm looking for on the boiling, you can put what I would recommend, here's this big square. Within this, you're going to draw a big circle that says, oh, here's this vapor pocket. Okay, you all seen water boil, so this is like a vapor pocket. So within this, you have water molecules that are very, very hyper, okay? They are completely free of each other. They're existing as a gas. Whereas over here, as the liquid portion of it, those are still bound together, okay? Now, when everything is a vapor, you're going to draw them all separately. You're going to draw big arrows that says, wow, these things have a tremendous amount of energy. So, on the first diagram, they're all bound together. Second diagram, some of them have broken apart as gases. The third diagram, they are all gas particles, okay? Now, when you get to this observations, okay, and here's the heart and soul of the lab itself. So what I'm looking for is that you're going, here's the hot spot, and let me lay out what I want. I say pay particular attention to how the particles will be aligned. Draw at least 3 symbols of each species. Okay, species is a technical term for what's happening in the solution. So you have 3 things. You have water, you have sodium, and you have acetates, okay? So these are the three things that you have. Acetates, sodium ions, water. And I tell you up there, what I want you to use for sodium is just a circle with a positive charge in it. The acetate, because it's so big, basically that's an oval with a negative sign in it, and the water is going to be a plus sign, a negative sign, with the two positives down here, okay? Now, think this through. The water molecule is going to have positive and negative charges. So those are going to exist like this. So you will draw those water molecules where you alternate them. Positive end of the water molecule is attracted to the negative end, so draw this alternating like this. The sodium ion, is it going to be attracted to the oxygen end of the water or the hydrogen end of the water?
Oxygen.
Why?
Because oxygen has a negative charge.
And the sodium has a
Positive.
positive charge. So what I would recommend is that you draw the water molecules first, and then put the sodiums and the acetates after you get the water molecules drawn. Now, but here's the deal. This is a liquid, right? So it's a liquid. So these particles can still move past each other. So what your ultimate goal that you're going to do in these diagrams, you're going to show me, here's the whole point of these diagrams. You're going to graphically show me the difference between how these particles existing as a liquid versus when you activate them and they form a solid. So basically what's going to happen is that you're going to reform that sodium acetate, okay? So what's going to happen is that the sodium and the acetate are then going to form bonds within themselves. The more bonds that you have, the more solid it is. So the difference between this as a liquid versus, I don't know where that string came from, versus after you activate it is the bonds that exist between the sodium and the acetates. So right now, they're not bound together. After you activate them, they are bound together. So when you draw it afterwards, show me, hey, I have more bonds. Okay, so that's the main thing that I'm going to look for in comparing the before picture and the after picture. Can you graphically show me that there are more bonds? Okay, because that's the whole point of this. And listen to me. When you form bonds, you release energy. So even if you didn't know anything else, as soon as you saw that sodium, if you felt that get warm, you're going to go, wow, I'm forming a bunch of bonds. The other cool thing about it is that you can visually see it turn into a solid. Okay? You're going to have two very macroscopic ways to show me and to realize that we're forming bonds. You're releasing energy, and you will actually see this thing turn into almost like a small hockey puck. Okay? Got the idea. Now, what you're after is the whole heart and soul of this thing is over here on page 3, question number 4. So, you're going to have the initial temperature of the water on page 2. This is over, I'm sorry, on page 3. You're going to have the final temperature of the water, and then you're going to calculate how much energy was released by that sodium acetate hot pot. So you're going to know the mass of the water, 300 grams. You're going to know your change in temperature. You're going to know the specific heat. You're going to calculate how much energy was released by this. There you go. Now, when you get to question 7 and 8 and 14, all of these are going to be dealing with this graph. Okay? So, this is the progress of the reaction. Now, I want you to look at this. So, down here on the bottom, over on page 3, okay? In this direction, I'm telling you the reaction is proceeding in this direction. On page 4, the reaction is going in the reverse direction. So in the forward direction, you're starting here. Here's my initial set of conditions. Here's my final set of conditions, okay? This is what's gonna happen with the hot pocket. You're gonna start with a certain amount of energy, okay? When you flip and bend the metal, that's the activation energy. That's like lifting it up, lifting that roller coaster up. Then the reaction's gonna start. You're gonna end up with less energy than where you started. The energy is gonna be given off as what we call an exothermic reaction. Now, if you reverse the reaction, you're starting here, okay? It's like now you're, the reverse is like you're running the roller coaster backwards. Now you're gonna start here, go up the hill, and then reverse it. So you have to look at the bottom to see which direction the reaction is going, okay? This one, you're starting there, you're going from left to right. On some of these, the reaction is going in reverse, you're starting from the right. That becomes your activation energy, okay? And that's gonna be the whole key to this. What's the difference in that activation energy? Okay, I'm done. So it's Wednesday, so here's what I want you to do. Don't worry about answering any of the questions. You have to get the data, okay? You can answer the questions later on. Get the data. So, get 300 milliliters in here. If you have this one, pour that 300 milliliters in here. If you've got this beaker, just keep it in there. Measure the initial temperature of the water, grab a hot pocket, grab it, boom, and then you literally like snap it. And so I just snapped that one. And what you'll see how that's like spreading out. And trust me, that's pretty warm. Actually, you don't even want to hold on to that, okay? So when you bend that metal, what I just did was I just lifted the roller coaster up and then it's going down a hill. Now, notice that that's pretty solid. Did I form a bunch of bonds or break a bunch of bonds? Huh?
Formed.
Yeah, I formed a bunch of bonds. Look, it's a solid. I formed a bunch of bonds. Guess what? It's also hot. Guess what? That also indicates that I formed a bunch of bonds. Okay, got it? Good, grand? Back we go.